Thank you. So I will talk to you today about quenching, because this is the quenching session. Specifically, we've heard already about quenching and its correlation with galaxy structure. I'm going to compare the importance of quenching with galaxy structure versus its correlation with the halo mass. So as we all know, the star formation properties of galaxies are bimodal. And the question is, how do galaxies quench? So Jerome gave a nice introduction to that. For central galaxies, of course, there are several ways that have been proposed in the literature to quench a galaxy. We heard about viral shock heating above a certain critical mass of about 10 to the 12 solar masses. The basic idea is that once a halo is above a certain critical mass, then it's able to sustain a stable shock which heats gas and may prevent gas from falling in to a galaxy, to the central galaxy, to continue forming stars. AGN heating is a process that is preferentially affects the hot dilute medium, so it's an internal process, a process that's internal to the galaxy, but it is coupled to the external halo. Also talked about in this conference is gaseous inflow into a compact bulge, which then leads to a starburst, which can lead to gas exhaustion, maybe, maybe not. And this process can happen in at least two ways, through major mergers or through inflow within a gravitationally unstable disk. Also proposed is morphological quenching, in which a bulge stabilizes the disk. Now, supernova feedback is also another way to quench a galaxy, but they preferentially affect galaxies that are less massive than the ones I'll be talking about, so I'll leave that out of the list. So, as I mentioned, viral shock heating is related to the halo, which is external to the galaxy. And gaseous inflow and morphological quenching are related to the galaxy itself, and they're related particularly to the morphology or galaxy structure. And AGN heating, as I said, is probably a coupling between a galactic process and a halo process. So any of these models could happen in combination or separately at different times. So the object of this is to try to learn as much as we can about these processes. Now, as for satellites, they of course could experience any of these quenching mechanisms when they were centrals, but they also experience mechanisms that are unique to satellites, such as ram pressure stripping. When they're moving in a hot medium, their gas can be stripped from their subhalos. Tidal stripping, which happens when they reach their pericenter, their orbit, as well as harassment, which involves high-speed interactions. So the object, again, is to learn about as much as we can about these, if we can learn anything about these quenching mechanisms. So what I'll be using to look at these kinds of questions is the Sloan Digital Sky Survey. Quenching I'll be defining as low star formation rate. So here I show the star formation rate versus stellar mass, and everything below this black line is quenched. And star formation rate is from the MPA group, and so is stellar mass. Halo masses are estimated from the group catalog of Yang et al. 2012. It's actually more representative of the group mass, the group stellar mass, but through abundance matching you can estimate the halo mass as well. Centrals versus satellites, that dichotomy is measured also through this group catalog. The central is defined to be the most massive member and the nearest to the mass-weighted center, and satellites are almost everything else. The satellite distance from the central galaxy is defined to be the relative projected distance over the virial radius of the halos, of the groups. And morphology or structure, actually, I'm only going to be talking about structure in this talk, is the central surface density that you heard about from Jerome. It's the mass density measured within the first kiloparsec of the galaxy. And some PSF corrections were done as well on these sigmas. Okay, so let's jump right into the results, okay? So here I have the sigma, which is the central density within the inner kiloparsec, versus halo mass, as estimated from the group catalog. And the white contours here are number density of points in the plot. And the color scale here is the quenched fraction. And if you can see, the black contours just follow the color scale. So what you should see here is that the quenched fraction increases very strongly with with the inner density at fixed halo mass. But you also see some, right at around the critical mass for quenching, the quench fraction is a little bit lower than other galaxies at high sigma. You can see this more clearly in this plot here, which is exactly the same except the color scale is now the specific star formation rate. And what you can see here again is that the specific star formation rate increases with halo mass. In other words, the contours are roughly vertical, as well as up here by the critical mass increasing with halo mass for high and low sigma. So these diagrams here may be pointing to two different mechanisms for quenching, one related to the galaxy structure and one related to the halo. Now let's look at this a little more carefully. This is for central galaxies. Did I mention that? I don't remember. Okay. Okay, so what I'm going to do now is take a window of halo mass and look at the distribution of specific star formation rates in bins of sigma. And so here I have it. We have a double peak distribution. That's our bimodality here. And the color scale goes redder as you get to higher sigma, so denser inner regions. And as you can see, the shape of the distribution changes. As you go to higher sigma, you get more galaxies in the passive peak of the distribution. But the overall distributions, the peaks themselves don't move right or left. The increase of the peak height or the decrease here is far more important in this diagram. Okay, so what about bins of halo mass in a fixed sigma width? So here you can see the same specific star formation rate distributions, and as you go redder in these histograms, that means you're higher in halo mass. So what you should see here is that the shapes of these distributions are roughly the same in these different mass bins, but they're marching along to the left to lower specific star formation rate. So, in short, the decrease of specific star formation rate is associated with halo mass, whereas the bimodality and where you are in the bimodality is associated with sigma. Now, we heard from Jerome about constant stellar mass bins being evolutionary tracks. So here I've plotted the same 6 bins that Jerome showed you, but instead on the y-axis I have specific star formation rate with quenched being at the bottom. Okay, so that's just to confuse you all and make sure you're all awake. Now, and the color scale here is the halo mass in each bin. Now, remember that each panel is a bin of stellar mass, so it also, for central galaxies, it's more or less a bin of halo mass as well. So the color scale had to change in each bin, but you can roughly see that if you are in the lower population here, you are going to tend to be in a higher halo mass bin as well. So, summary of results for central galaxies. Sigma determines the quenched fraction of central galaxies, roughly, and the halo mass determines specific star formation rate. So how do we interpret these results? Okay, so I'm going to propose a simple ansatz, basically that the increase of the quenched fraction is related to the transfer across the bimodality, okay? So assuming that galaxies do transfer from one peak to the other peak, that transfer must be quick because otherwise we wouldn't have such a low valley. However, the decrease of specific star formation rate is related to the slower fading of star formation. So if these assumptions are correct, then sigma is related to a fast quenching with shorter time scale, and halo quenching is probably slower, or halo-related quenching is slower. Okay, so now this makes sense because viral shock heating is expected to cut off accretion, but remaining gas in the galaxy is expected to continue forming stars. And this process can take 2 to 3 gigayears, as we've been discussing, maybe even higher at higher redshift. However, mechanisms that result in high central density, namely mergers and violent disk instability, are expected to be rather violent. And once gas is consumed in these kinds of processes, halo mass could play a maintenance role by preventing new gas from falling in, keeping it hot. These ideas do need to be tested. This is very speculative. They need to be tested, although initial tests that I have run in a particular SAM do look promising. So, okay, so that was central galaxies. Let's talk about satellites. So here I'm showing the relative distance from the group center on the y-axis relative to the virial radius versus the halo mass of the group that the satellite is in, and colored by the quenched fraction. Now, as you can see, quenching for satellites increases with halo mass and decreases with relative distance to the group center. Now, if you make the same plot, but switching the x-axis to stellar mass instead of halo mass, you can see that in the outer regions, far from the center, the quenched fraction increases rather strongly with stellar mass, but almost not at all in the inner regions. Now, in the outer regions, this is where the halo quenching is the weakest, but still non-trivial. Satellites here probably likely fell in recently, and so may not have had time to experience the slower halo quenching. And satellites close to the center fell in less recently, and their quench fraction depends strongly on host halo mass. So keeping these regional differences in mind, I've split up the satellites into 3 regions: the outer region, the intermediate region, and the inner region. And I'm going to compare the quenching dependence on sigma of each satellite versus the halo mass that it's in. Okay, so this is it. So sigma versus halo mass, like we had for the centrals, but split up into 3 distance bins for satellite galaxies. Now, as you can see, the quenched fraction in the outer part of the halo depends on sigma very strongly, but no, this is for the satellites. These are for satellites. The halo dependence is non-trivial, but of course the sigma dependence is quite a bit stronger. Now, as you move towards the inner parts of the halo, then the quenched fraction depends almost entirely on halo mass. And in fact, if you can see here, the color scale tells you that about 12.8 here in this scale, almost all of the galaxies' satellites are quenched. So this 12.8 is higher than M-crit, but this might possibly be explained by the fact that quenching in halos might be delayed. So, in summary, the results for satellites. In the outer regions of halos, sigma dominates the quenched fraction. Satellites only probably recently fell in and have not had time to experience the slower halo-related quenching. And keep in mind that galaxies that, if this is correct, that there's a slow mode and a fast mode, galaxies that are on the slow mode can easily move to the fast mode, for example, through a merger. However, galaxies on the fast mode that already quench probably can't move back on the slow mode. So that's probably what we're seeing in the outer halo for these satellites. In the inner regions of halos, the halo mass dominates the quenched fraction, and almost all satellites are quenched for halos above 10 to the 12.8. This is slightly greater than M-crit, perhaps due to a quenching delay. So in summary, both the halo and the central density play a role in quenching, particularly for both centrals and satellites. For centrals, the sigma determines the quenched fraction, which might indicate a quick transition from being star forming to being quenched, whereas the halo mass determines specific star formation rate. So this might indicate a slow fading of star formation. For satellites, halo quenching happens in the inner halo, since the halo quenching is slow, and nearly all of them are quenched above a few times M-crit. And sigma-related quenching, which is probably the fast mode, affects satellites in the outer halo. And that's it.
Thank you very much for keeping time. Yes. Okay, questions and comments? Yes, Charlie.
One might want to be careful about overinterpreting what's happening in the inner regions of these halos, especially at the big group and cluster scales, because it's often really non-trivial to distinguish between a central and satellite in these catalogs. They often have similar masses. I mean, you look at Virgo and Coma, tell me where the central object is just from the optical optometry. So, that could easily smear out a lot of things in the regions in terms of trying to pull apart satellites from the centrals.
Yeah. Statistically, though, for the satellites, they're probably more likely a satellite than a central. It's the central that will probably more likely be wrong. Correct?
In the inner regions, when you only got 1 or 2 satellites, it's not so obvious.
Okay.
Yes, please.
So you used the term halo mass quite liberally there.
Yes, I did.
We know that you're not actually measuring halo mass.
Yes.
You're measuring the total group stuff.
That's right. Yes.
Have you thought about how the scatter between that and halo mass impacts your conclusions?
That's a good question. I have not. That's a good question. I should note that and keep in mind.
There is significant scatter.
Yes, that's true.
Some is quantifiable, and that will presumably strengthen the true results of halo mass.
Presumably, yes. Yeah. So because
Can be confused with being slow.
right.
The scatter can be confused with slowing down, right? Exactly.
So some of the slowness can be scattered.
Can be some of the scatter. Right. Okay. That's true. Good point.
Yeah, you.
The group results suggest for central galaxy, the central surface density is basically because
Yeah.
the value of the
Mhm.
bimodal distribution haven't been at the same signal.
Yeah. More or less.
It assumably suggests, or it implies the size of the galaxy and mass of the galaxy. Because not only specific transformation rates correlate with that, but also the size of it.
Mhm.
Assuming all the transforming galaxies have certain profile, then for goodness data mass, and you have a certain size. So all this correlated quantity is have you tried to do a certain profile and whether you can
Well, it's true. All these quantities are related. Sigma is correlated with halo mass, which is correlated with stellar mass, and all these things are correlated. So I tried to keep within bins. I don't know if you caught that, but with those histograms, I tried to keep within a bin, a narrow bin of halo mass, and a little bit wider bin of sigma for the second plot. So I didn't at all take into account sizes, though. I wonder if that might take. Yeah.
Actually, I have a question.
Yes.
So you find that the surface density plays a very important role. Then, when we try to understand the evolution from, say, the blue cloud to the red sequence,
Yeah.
and how do we do that? I mean, the blue
Yes.
cloud usually is
Okay.
quite diffuse, right, in a
Yes.
sense.
Yes.
And then we merge or evolve. How can I evolve and merge into something that actually is more dense?
Right. So, okay, I haven't taken merging into account, but so in Jerome's plots, this is my version of Jerome's plots, in the assumption of evolutionary tracks here, this works because the assumption is when you're quenching, you're not going to change much in stellar mass. That's why they're evolutionary tracks. But that's only true if you're quick quenching, right? So there could be a quick path going this way, and then there could also be slower paths where the stellar mass does increase, and then they move to the next bin here, and so there could be a mix of evolutionary tracks. And I don't think that it's particularly one way that we quench a galaxy, but there could be a population that are mixed by or that are quenched by different ways, and the population is mixed.
I always find it difficult if you can change something that is fluffy and then become more compact. That for me is very difficult to do.
Yeah, there is dissipation and
dissipate, right?
and there was
If it's a dry merger, where the dissipation come from?
No, dry mergers don't do this.
Yeah, that's right.
Wet mergers do it.
Yeah, so that
Yeah.
basically says that a lot of things will actually have a starburst before it moves to.
That's the blue cloud,
yeah,
Okay.
yeah.
Okay,
yeah.
good.
Blue, that's
Yes, Abhishek.
back to the results of Thomas Thal, I didn't mention it, I think, but if you ask, is quenching of satellite central, at what halo mass do they happen? It turns out that they happen roughly the same few times 10 meters for a mass.
Mhm.
That's Joanna. So I think these results are very consistent.
Yeah.
Okay, so let's move on.